maybe just to get you all in the mood of math again, because probably you slipped out of it if you were in the mood for math. Let me show you the thing that I watched at the beginning of the year, the Babylonian algorithm. So this is this thing known to the ancient Babylonians, 3,000 years ago, how to calculate square roots in your head. Okay, so square roots in your head. Mental calculation of square roots. So here we go. Somebody give me a number between 1 and...
I just had to get my keys.
Sure, no, I can see. Go ahead. Okay, so somebody give me a number between 1 and 100, say?
27.
27, okay. So I'm going to guess that the square root of 27 is something like 5 point... wait, let me make sure I've got it right this time. Let me make sure I got it this time. So 5 and 2, that's 5 and 1, that's 5.2. Okay. That's going to be, I hope that's the right... Wait. Let me think for a second. Is it right?
5.196.
Okay, 5.196.
Don't scare.
Okay, so I was off by, so this is off by, say, 0.004, right? So that's not bad, right? For guessing. So what did I just do? Yeah, Lauren, you know?
So you went to the closest square root you could think of, which is like 25, and so you knew it was going to be 5 point something.
That's right, it's going to be 5 point something. There's actually, the trick is actually a bit better than that. And come to think of it, it's in fact sort of an application of the midpoint formula, which I made fun of as useless earlier. It's not really the midpoint formula, but it's an averaging. So here's the idea. So if you knew the square root, right? So here is 27. Okay, here's 27. Right? If you knew the square root, right, then you would have the lengths of a square, right? You would have the lengths of the square. This would be root 27, and this would be root 27, right? Right. That's obvious, right? But you don't know that. Okay. So what you do rather is you say, okay, here is my 27, and I'm going to make a guess. Okay, my guess is 5, right? Because 5 squared is pretty close to 27, right? But you know that 5 is actually too short. It's not the right length. It's too short to be the square root. This side is going to be a little bit longer. What's the length of this side? What's the length of this side? If the area is 27, this length is 5, and what's the length of this side? Laura?
27 over 5.
27 over 5, right? 27 over 5, right? Or 5 and 5 and 2 fifths. 5 and 2 fifths, right? Okay, so then you say, well, this side is too short, and this side is too long, right? If it's not the square root, if it's not the true square root, then one side's going to be too short and one side's going to be too long, right? So you know that the true square root is going to be maybe somewhere between them, and so you take an average. Right? You take the midpoint, or you take the average of these two guys, right? So 5, right? 5 plus 5 and 2 fifths over 2, right? 25 fifths plus 27 fifths over 2, right? Which turns out to be 26 fifths, right? Or 5 and a fifth. 5 and a fifth, and this is a 5.2. Right? And so that's the first guess of the Babylonian algorithm. And then you can actually keep on going. You can say, okay, now I'm going to make another guess. The second guess is going to be this 26 fifths. Right? 26 fifths, and this is 27, right? And then so what's the length of this side? Well, it would be 27 over 26 fifths. Right? In other words, 5 and 5 26ths. Right? So your second guess would actually be, so then you say, okay, well, again, one side is too long and one side is too short. So you take the average, right? You say 5 and 5/26 plus 26/5 over 2. Okay, I can't do that one in my head. But if somebody would like, so right, so this is 5.2. This is 5.2, right? Can somebody do 5/26 on the calculator, just so that we don't have to.
0.192.
192, something. Okay, so you take the average of these two lines, right? And the average would be, 5.196, right? The average, the distance between these two guys is 0.008, so the average you add 0.004 to this guy, right? And so the second guess would be 5.196, right? Which is very close to the actual square root. Right? And you just keep on going.
This isn't mental math anymore.
The second step isn't, but the first step I think is.
Okay.
Right? The first step, right? You say, okay, I'm going to make a guess of 5, and then I'm going to take 5, and then take 5 and 27 over 5, and then I'm going to divide that thing by 2. Right? That's what I think you guys can do. So, shall we try one? Just for fun?
Okay.
Okay. How about okay, so now you have to do it in your head. You have to do it in your head. Okay, so that's the game. Okay, so how about 18? 18 is sort of along the same lines. Can you use a pencil? Can you use a pencil?
Maybe only 4.45.
4.45? 4 point. Right. So what do we have to do?
4.25.
4.25. Great. Actually, 4.25. Right, because 18, you get your first guess would be 4, right? Your first guess would be 4, and then you'd say, okay, I'm going to take 4 and 18/4, right? 4 and 18/4, and then divide that thing by 2. But sometimes it's easier to write this guy as 16/4. 16/4 and 18/4 divided by 2. The average of 16/4 and 18/4. Well, the average of that is 17/4. Right? Well, the average is going to be 17/4. That's the same 4 1/4, like 4.25. Caroline, if you square 4.25, what do you get on your calculator?
18.625.
So not too bad. Not too far off. What's the actual? I'm sorry, don't bother you again, but what's the actual square root of 18?
4.2426.
4.2426. So again, we're off by 0, 0, 7, 4. So that's not, again, it's not too bad. So this is what I do when I'm driving, and like Mom says, stop doing that. You're gonna crash. Because I actually try to do it to the second place. I try to do 2 iterations. The first iteration is easy, the second iteration is not easy.
Can you do that while you're driving?
I do. It's actually not a good thing. I do it when I'm driving or when I'm down. Just to cheer myself up. At least I can do something. And also I think it's good practice this, right? To be able to keep a lot of things in your head at the same time, right? This business of being able to have an entire complex thing running in your head. That's actually a useful skill in any field, in mathematics, and I would think in anything, being able to do this. Okay, so that's the Babylonian algorithm. Like I said, known for thousands of years, incredible. Okay, so let's go on to section 4.5, which is what you can think of as optimization. Okay, so getting information out of the mathematical representation. Okay. So last time we had these problems, right? And we took the problems and we changed them into mathematical terms, right? So last time you had some physical problem, and then you got out of it the mathematical structure. So underlying mathematical structure. And this time we'll use the underlying mathematical structure to get info about the problem. Okay, this is a game that is often played in math. We're not going to play the full game. We're only going to play it in the case of quadratic functions. Okay, so when you get to calculus, then you'll learn how to play the game for like a wide range of functions. But right now we don't have the tools. We don't have the derivative. The way of measuring where the instantaneous velocity, Okay, so we're going to have to use only calculus. We're going to have to only use precalculus. Okay, so only quadratic functions, and let's recall, if you have a quadratic function, f of x is ax squared plus bx plus c, right? Then the vertex occurs when x equals negative b over 2a. The vertex occurs when x is negative b over 2a, right? Is that obvious? Can anyone explain it to me? Why do we know that the vertex typically?
Because when you're completing the square, you have to divide by 2, and then that's...
Exactly. So why? Because of completing the square.
So if you know how to do that, you never need to complete the square.
If you're looking for the vertex, yes. If you just memorize this fact, then and somebody says where's the vertex, then you wouldn't have to complete the square to do it. But you get more information from completing the square as well. So let me just make sure that everybody knows what Tiffany knows. We'll do completing the square on this guy. We'll say a x squared plus b over a x plus c. Right. We'll rewrite it. Right. And then we do completing the square on this thing. Right. We say a. Well, this is kind of remember we have to add on b over 2a. B over half of that line squared, right? And we subtract off again half of that line squared. See? Okay, and then this thing turns into, right, this part turns into, right, x minus b over 2a quantity squared. Right, and we see that that the vertex is when x equals b over 2a. Okay, is everyone okay with that? Everybody shut your eyes for a second. Open, raise a finger if you're not okay with this. Thank you, great. Open your eyes. Everybody's okay. Okay, right, so, and you notice that, right, if A is positive, then this is a going up parabola, right? So this is where the minimum occurs. This is where the minimum value occurs. Right? And if A is negative, then this is where the maximum occurs. Right? Because A is negative, then it's going down parabola. And the thing has a max at the vertex. Right? Okay, so this is a way of finding where the max or the min of the parabola is. Right? Okay, so this is what we call optimization. Finding the highest point, finding the smallest point, okay, if there is such a thing. Okay, so let's do a simple example. This is number 10 from the homework. You have a h of t is 512t minus 16t squared. Okay, and this is actually the height of a projectile tossed into the air. You may know if you've taken physics that any projectile tossed into the air will make a parabola, right? If I do this, that's basically a parabola, right? That's something very nice. Okay, so here is a parabola that is described by a quadratic, right? So here's a quadratic describing the behavior of some projectile, and the question is, what is the maximum height of the object? What's the maximum height of the object? Okay, so take 2 minutes and see if you can figure it out, please.
Is that 512?
512.
Is it in feet?
Yeah. Okay, and feel free to talk to each other. I'll step out.
Yeah, it gives you 16 and you put
Is it
16. Yeah, you get 16 and you put 16.
Negative?
No, because it's negative. Oh,
Negative
negative.
B would be negative.
Yeah, it's negative 16, and then I'm just going to plug it in at 15. No.
Sophie, how about you?
I haven't finished it yet.
Okay, well, let's start with this. So how do you, you're trying to find where this function is the biggest, right? It's a downwards going parabola, so what do you do?
So you have to put it into the form where you can find different. You have to take out -16 so that, and then you have to include the square.
Oh, okay, so you're gonna actually go through the whole process. Okay, that's fine. So you say, let's take out the -16, right? We get t squared minus, what is that? 32? T squared minus 32t, right? And then you complete the square, say, and you get t squared minus 32t. Half of that squared is 256, right? And so you get -16 t minus 16 quantity squared minus 256. Right. Okay, so you do completing the square, and what does that tell you?
Tells you the vertex,
The axis of symmetry?
the axis of symmetry is 16 and 16 times -16 times -256.
Oh, okay, you're talking about the vertex. The
Yeah,
vertex,
then
yeah.
from there you can.
Yes. Okay. Right. So from here, what do you see? You see that right, the vertex occurs at t equals 16. Okay. The vertex occurs at t equals 16. Right. Here you see that the axis of symmetry is at 16. We could have we could have just used what we worked out. And said, well, it's going to occur when t equals -b, right? -b over 2a, right? Which is 16. Okay, so
And then you just plug 16 into t.
and then just plug 16 in, right? So at that point,
I think it's
-4,096.
-96.
That time, h of 16, right, is going to be 512 times 16 minus 16 times 16 squared, right? Whatever that is, which is probably -4,096.
So the vertex is 16.
Wait, it should be positive 4,000.
Yeah, that's what I'm saying.
Positive. Right.
Ooh.
Oh,
Because you flip the sign?
You probably missed the sign.
No, it's not even done. Just keep,
You
for the second vertex, you don't flip the sign like you do for 16.
you just take the 16 and put it back into here, right?
Oh, the thing is, I got -16 when I did the vertex.
No, that's not right. It should be 16, right? Because
It's -16a.
what were you doing, Alex? Did you do complete the square, or did you use?
No, I did a negative b over 2a.
Okay, right. So the b is 512, and then the a is
Shouldn't that be negative? Yeah, but,
a is -16, right? So b,
so negative, I see.
right, negative b over 2a,
Okay.
right?
Yeah. And so it's positive.
Yeah.
So the vertex is at 16, comma, 4,096.
That's good.
Okay.
Okay. So you know where this object is going to be at its highest point.
Okay.
Okay. So all of the problems in this section are basically two-part problems. Yeah.
When you ask for a maximum or minimum, do you want it in a point? Like, do you want us to, like the final answer, do you want us to give you the actual point? Or do you want us to just give you the y value?
So the h is the y value.
Right.
The h is the y value. So in this case, if I'm asking what's the maximum height, then
So
that would be
then, the y
that would be
value.
the y value.
Okay.
Okay. But if I asked for what's the time and the height, then that would be 16 and 4,096.
Okay.
Right.
Thank you.
Other questions? Okay, so like I said, all these problems have two parts to them. The first part is this part, basically what we did in 4.4, and then find out where the thing retains a max or retains a min. Okay, so let me give you an example. So two numbers add to 9, and let's say that they are, two numbers add to 9. What's the largest value of their product? Okay, because so you've got a game here, right? Everybody's allowed to choose two numbers that add up to 9. Okay, and the person who gets the two numbers that have the biggest product wins. Okay, two numbers add up to 9. So you might think, 8 and 1, and that will give you 8. Right? 3 and 6, that will give you 18. Maybe you can guess it already. What do you think it's going to be? Two numbers add up to 9. 5 and 4, that give you 20. It's getting bigger.
4 and 5.
That's what I do to my daughter. Yeah. Okay, what's 5 plus 5? Okay, now it's 4 plus 5. It's the same! But it took a while to get to that point. Like, after doing it many times. Let's do this. Finally, she realized it would be the same. Yeah, it's not obvious at the beginning.
It's like the closer the numbers are, then the higher the product will be.
That's what it seems like, right? It seems like the best thing to do is to choose numbers that are as close together as possible. In other words, 4.5. Right? So that's your guess, and let's see if it's true or not. Right? So remember, we actually did this sort of thing last time, right? Right, we had we have to play the same game we did last time, right? We have two numbers, x and y, add to 9, right? X plus y, x and y to two numbers. X plus y equals 9, right? In other words, y is 9 minus x, right? And we want to maximize x times y, the product. Right? Let's call P the product. P the product. Okay? We want to maximize that thing, right? But the first thing for us will be to express it as a function of one variable, right? And so we want to get rid of like what we did last time, we want to get rid of one of the variables, right? And we see that if we call the first guy x, then we can write this as x times 9 minus x. Right? We did this last time, so this should be old hat. Right? So the product of x and y really depends on just the first guy, of course. Because once you know the first guy, you know the second guy, and you know the product. Right? If I tell you that the first guy is 3, you know that the second guy is 6, and that the product is 18. Right? I don't need to tell you both numbers. Okay? Okay, so now what do we do? Well, this thing is a quadratic, right? This thing is a quadratic. It's negative x squared plus 9x, right? And the question is, for what x is that maximized? Right? Right? And we know, right? For what x is it maximized? negative b over 2a.
So it's -9 over -2.
Right, negative 9 over negative 2, in other words, 9 halves, right, 4.5. Right, that's what you guessed. Okay. So this is a physical problem, right? Somebody gives you a wire of length 9 and says, you know, how shall I bend it? How shall I bend it so that I get the maximal area? Right? How shall I bend it? At what point do I bend it to get the maximal area? Right? And you can sort of see that, you know, if you bend it at the end here, you know, your area would be pretty small. Like if you bend it just a tiny bit, then your area would be very tiny, and then, you know, you bend in the middle, it'd be the biggest here, and then it gets smaller from there onwards. Just in the class that I was, in my other class that I'm teaching, so the other class I'm teaching is called Fourier analysis. This has to do with the mathematics that underlies music compression, like digital music or digital imagery. And it takes Fourier analysis to answer a question like this. If you have a wire of a fixed length and you're allowed to bend it into any shape, what shape has the maximal area? Okay, so you have a new competition, right? Everybody gets a piece of wire and you're allowed to bend it into whatever shape you like. You know, what shape is best? And you can probably guess what best shape is best. What shape is best? A circle. Yeah, it turns out to be a circle. But it takes a bit of more high-powered math to actually show that that is the optimal shape. So this is like the beginning. What we're doing now is the beginning of that. Okay. Okay. Everyone all right? Right. So, you know, we played the game that we did last time, and then now we play the new game. You know, where is the function biggest? Right. Turn the problem into a function, and now we optimize the function. Okay. Yeah. Okay. Okay. Okay, let's do two more examples. So here is an example. I think this might be an example in your book. So you've got two roads. For some reason, somebody has built roads according to mathematical formulas. Okay, and so the first road follows y equals x to the fourth plus 10. The second one follows y equals 4x squared. Okay, and your job is to build a road at some point, x. Okay, and the question is, where do you put the road to get the smallest, to use the least material? Okay, so what x do we choose? Let's call this thing L to minimize L. It's actually not so strange to build roads based on mathematical formulas. There's one built on something like x squared, x cubed plus y cubed equals z cubed, or something like that in Europe. Anyway, there are roads built on mathematical principles. This is not really relevant, but on Facebook I saw that there was a school built according to the layout of the Millennium Falcon. Like they didn't realize it, but the person who designed it laid it out so that from the sky it would look like the Millennium Falcon.
They definitely did that on purpose.
Oh yeah, for sure.
Why would they? So the first thing to do is to express L as a function of x.
right? What is, right, L depends on x, right? And then you have to minimize L. Right, as x changes, L changes. Right, L depends on L depends on x. Right, is a function of x. Okay, so let's see if anybody has ideas, right? What is L of x? What is L of x? Carol?
L of x is the distance between the two rows. So it's the distance between x to the fourth plus 10 and 4x squared.
Right, so you just subtract one from the other, right? So it's just going to be this height, which is x to the fourth plus 10, minus the lower height, minus this height, right? This height is 4x squared. Okay. So we get x to the fourth minus 4x squared plus 10. Okay. Right. And we're trying to minimize that. Okay, so what's the difficulty? Is there any difficulty? There's one trick involved. What's the trick? Lauren?
Well, it's not really quadratic.
It's not a quadratic, that's treble, right? Is it treble?
No, because you need to
No.
factor out x squared.
Substitute.
Where t equals x squared.
Yeah, let's rewrite this as, L of t, saying L of t is, where t is x squared, t squared minus 4t plus 10. Right? And we know we can minimize that by finding its vertex, right? Where is its vertex? And vertex at what? Two.
Oh,
right?
2.
2. Right? 2. Negative b, that's 4 over 2a. Negative b over 2a. So t equals 2, right? So this time, so L obtains minimum value at t equals 2. At t equals 2, right? Our question was about x, right? So at t was x squared, right? So this is when, i.e., when x is equal to root 2. Okay, who can use the Babylonian algorithm to get a good approximation of root 2? Well, your first guess would be 1, maybe. And then you take 2 over 1, that's 2. And then you average them. You get 1 plus 2 divided by 2. 1.5, right? Which is something like 1.5. Actually, that's pretty bad. 4142. But anyway, so the answer is when x is equal to root 2. When I was young, calculators didn't have a square root function. So I actually spent much of my childhood punching in numbers and trying to get farther and farther, greater and greater degrees of accuracy. you know, like, okay, what's the next number? Like, just punch in numbers randomly, you know, and see which was high or low. This is my entertainment.
So you don't need to find the other value?
Whatever.
Well, because you just found, aren't you supposed to find the vertex?
No, you're supposed to find the place x where L is least. Right? And we found it. What you could calculate is, what is that length?
Yeah.
You could, but that wasn't the question.
I don't know why, but I saw them equal to each other and it still work. Should I just not do that and just
Set
submit that
them
one?
equal to each other. You set them equal to each
Like
other.
4x squared equals x.
That shouldn't work, right? Because that will tell you where the two lines intersect each other, right? That'll tell you the x for which there must be some.
Because it works as 1 minus the other, so that's the same as 1 equals. You add.
So you use the zero side properly.
So if we added 4x squared to both sides, you have 10%.
No. Right, you set them equal to each other, so 4 plus 10 equals 4x squared, right? And then you get x to the fourth minus 4x squared plus 10 is equal to 0. You play the t substitution, t squared minus 4t plus 10 equals 0, right?
So that's saying L of x equals 0.
Yeah. Right, that's where L is 0, right? That'll just tell you where they intersect each other. It should not have worked. You must have made two mistakes, and they canceled each other out. So the moral is always make two mistakes. Okay, last example, and since there's not too much time, let me do it for you. And this one is the trickiest one. Problem 29 next. So somebody gives you a square, and the side length is 1. Square of side length 1, and inside here, you do something like this. So t minus t, t. So on each side, you divide it into t 1 minus t. So you get the square in the middle. You get the square in the middle. Okay. So the question is, to find, let's call this length x. And the question is to find the x for which the area of the square is minimized.
The area of the inside square?
The area of the inside square is minimized. Okay. And maybe it's, actually, let me leave this x out. I'm going to quickly find the t for which the area is minimized. And again, you can probably guess, right? What's going to be the answer? What t is going to give you the smallest square on the inside? If the total length is 1, okay, what is the answer?
If it was 1 minute, it can't be 1.
The area for the guy in the middle inside, you want to make this one as small as possible. Okay. So you notice if I take my t to be really tiny, then I'm basically going to eat up most of the square, right? The thing is huge, right? So And if I take my t to be too big, then the same thing happens on the other side, right? So again, it's going to be something in the middle. It's going to be a half. Okay. So you'd say, okay, let's call this thing A, right? A as a function of t, right, equals what? Well, we have to figure out what is this length here? You know. By the Pythagorean theorem, right? By the Pythagorean theorem, we see that if this is x, right, x squared is equal to t squared plus 1 minus t squared. Right? And so the area is actually t squared plus 1 minus t squared, 1 minus t quantity squared.
Wait, do I have to take this square?
We have to take the square root, but then to get the area, we square it again.
Okay.
So we come back to that. Right? And you work this out, it becomes 2t squared minus 2t plus 1. Right? And we see that it's minimized when t equals negative b over 2a. In other words, a half. As we intuited. Okay, so like I said, the actual story is much, much deeper than this. You'll get to it when you take the next course.